So our next speaker is Ulrik Buchholtz, and his talk is on epimorphisms and acyclic types in univalent mathematics.
Yes, thanks so much for having me. As Egbert mentioned already, we're thinking about acyclic types, and this is closely related to epimorphisms, and this is going to work with Egbert and Tom, who's also here. Okay, so let's, what is it all about? So I think the project started with Tom and Egbert thinking about epimorphisms in homotopy type theory, so we're working internally, and this is a good definition in higher category theory. So you don't ask for the precomposition map to be an injection, you improve it to be an embedding, and that tells you that whenever you have an extension problem along F, for any map from A into X, and you want to know if it extends along F, then that extension problem is an embedding. The type of all extension is in propositions. Okay, so that again, it says that extensions along epis are unique if they exist. Okay, so that's one ingredient in what we're studying. The other thing is acyclic types, and this was what Egbert mentioned this morning. An acyclic type is one such as when you suspend it, it goes poof, becomes retractable. So we want to relate those two things, of course, there's a notion of acyclic maps, right? So we define this fiber-wise, like connected maps to truncated maps. So an acyclic map is when all of whose fibers are contracted. So here's a basic lemma about epimorphisms that's completely parallel to the one category case. The map is an epimorphism if and only if the square formed like that, with the map with itself in the identity morphisms in the codomain, this is push out. And if you stare at this and you think about what happens to map to the terminal object, that gives you the relation to suspension. Right? The suspension is defined as the push out of the terminal projections. Right. So here's the basic lemma. If you calculate the fibers of the codiagonal is the co-gap map for such a square. So the fibers of the codiagonal are the suspensions of the fibers of F. And then we directly conclude that a map is an epimorphism if and only if it is the same. That a little bit. The good news is I only have 7 slides. The bad news is that they have a lot of stuff. All right, so I wanted to talk about some things. So the slide, I just uploaded the slides on my webpage. So if you want to digest them later, you can do that. Right. Okay. So what is an example of an acyclic type? So obviously, the unit type is acyclic because its suspension is an interval which is contractible. And we can also conclude some basic things about acyclic types. They are all connected, and the fundamental groups are perfect. In fact, the fundamental groups are super perfect. So what does it mean to be a perfect group? It means that your abelianization is trivial, and the abelianization is what you get when you suspend. You take a type with the fundamental groups in the group. When you suspend the type, you get something with pi2 being the abelianization. That's the connection there. Okay. So here's a non-trivial example of an acyclic type. I want to give you a non-trivial example early on, so it's not just the unit type, because you can give very complicated talks about the unit type, but that's not what we're doing here. So here's an example of an acyclic type found in the Hatcher's algebraic topology textbook. And we can directly encode the corresponding type as a higher inductor type. So it has these constructors. There's one point constructor. There are 2 loops at the point A and B. And then there are 2 higher path constructors and 2 path constructors. One says that A to the 5 is B to the 3. And the other says that B cubed is AB squared. Okay. So it looks, maybe if you know something about icosahedra or dodecahedra, that's a bit related. There, if you rotate, I guess a dodecahedron around the center of its face, that's a 5-fold symmetry. Here we don't say these are 1, but it's actually quite closely related to icosahedra. Anyway, it's very easy to see that this type is acyclic. What you do, you can rewrite the suspension of it as another hit, because we're taking a co-limit of a co-limit. So it's just push everything up. So now you have point constructors north and south. The meridian splits into these constructors. The meridian at a point is the path from north to south, and then you just have all the other constructors one dimension higher. So now you have A and B are 2 paths, and the R and S are 3 paths. But in a double loop space, we have the Ekman-Hilton construction, which is a construction that equates or identifies AB with BA for any 2 elements. So in this type, we can rewrite the type of S. It's equivalent to say that B cubed is A squared, B squared. And then the path type, if you have any fixed path, you can concatenate with that. That's an equivalence. So S is equivalent here to B equals to reflexivity. B is A squared. B is A squared, and then you contract it. Then you have a constructor B, and say B is this thing. Then you can contract it away, and then the other constructor then simplifies to A to the 5 is A to the 6, which is equivalent to ref equals A, and then it goes poof. It's gone. There's just the point left. All right, and in fact, as I mentioned, there's a homomorphism onto BA5, which is the classifying type of the rotations of an icosahedron, but it's also the classifying type of A5, the alternating group on 5 letters. And this is obviously a group epimorphism, so it subjects onto the group. So this map on types is 0 connected. So that means that X must be it's not contractible. Okay, there we go. That's that slide. Closure properties. Let's see. So you have some basic facts. I won't bore you with all of it. So let's see. You have 2 out of 3 that you not full 3 for 2, but only the one where you get the last map if you have the composite and the first one. And let's see, you can acyclic maps are closed under pullbacks and push-outs along arbitrary maps. And they're stable by composition, retract, finite products, and limits in the arrow category. So, but of course, not the acyclic types themselves are not closed under the pole limits in the arrow category, but the types are not closed under the acyclic types are not closed under pole limits. For instance, I said they have to be connected. So 1 is acyclic, but 2 is not acyclic. It's not connected. Okay. You don't have to read all this. This is just, I want to indicate that there's some classical interest in acyclicity connected to algebraic K-theory. And this also provides a counterexample in the classical model to what you might hope that a truncation of an acyclic type is acyclic. Doesn't happen. You can have an acyclic type whose one truncation is not acyclic. Right. There are lots of things we would like to prove about acyclic maps, but we don't see how to do it without some extra assumptions. So one such assumption is this plus principle. One thing so this plus principle holds in every model we've thought of. It says that every acyclic and simply connected type is contractible. And this was introduced in a note by Markoios about similar things in infinity topos theory. And he leaves it as an open problem whether it's just true in all higher toposes. It follows from Whitehead's principle. Whitehead's principle says that infinitely connected things are contractible. And we have a lemma that we can prove outright that any acyclic and simply connected type is infinitely connected. In fact, this is so short that I put it in the abstract. If you want to see the proof of that, that's in the abstract for this talk. But it also holds, so there are lots of models where Whitehead's principle fails. But the ones I've checked, we've checked the plus principle is still true. So maybe if someone some idea for where it might fail, or maybe some idea for showing that it holds outright, either in all broken infinity toposes, or maybe it's provable in hard outright. We don't know. Anyway, let's assume it for some things and see what we get. So one thing is we get the relative version of it. So the principle says that simply connected and acyclic is contractible. The relative version says one equivalent acyclic is an equivalence. So one equivalence means that you get an equivalence in the one truncations. Right. So I mentioned that we introduce epimorphisms in order to figure out when an extension problem is a proposition. And we would like to know, what is this proposition? What can I now check to know that I have an extension along an epimorphism? And the proposition is this, that you can extend f prime along an epimorphism, an acyclic map f, if and only if you have this condition on the kernels on the fundamental groups. So that the kernel of pi1 of f sits inside the kernel of pi1 of f prime. You can either read that as an inclusion of relations or as an inclusion of subgroups for every chosen base point of A. And this is pretty easy to prove from the plus principle. You take this push up, you want to know if there's an extension from of f prime that takes a map from B to X, so that the composite is f prime. So you take the push up, then a little computation. So I mentioned that acyclic maps are close on the push up. G is an acyclic map, and computation with Van Kampen says that this is a one equivalence. And if G is an equivalence, then you get your extension as by taking the map from B to P and going by the inverse. And the condition is obviously necessary just by, because if you have it by functoriality of a fundamental group functor. Okay, here's something we were struggling with for a long time, which was to provide a different example than this one from Hatcher. There's this famous example of an acyclic type coming from a group, the Hickman group. And the Hickman group has this presentation of 4 generators and 4 relations. And all of the relations say that every generator is a commutator, specifically the commutator of the element before in a cyclic order and the element. So it's like you go A, B, C, D, A. You have a cyclic set of generators, and the relations say that everything is a commutator in this way. So if everything is a commutator, then the commutators generate the whole group. So the commutator group is the whole group. So it's certainly a perfect group. So it's plausible that the classifying type is perfect. And in fact, it is perfect. And even better, which I will show without any assumptions in constructive, but this presentation is already the classifying type. But usually when you take a group presentation and you make the classifying type, you add these constructors, a point constructor, a path constructor for all the generators, and a 2-path constructor for all the relations, and then you one-truncate. But the beautiful thing about this presentation and all so-called aspherical presentations is that this hit already is the one type. And that happens here, and we'll show that. So the first thing to notice is this type is acyclic, and the proof is just like for Hatcher's example. You look at the hit for this suspension, and then it goes just in the same way. You can contract away pairs of 2-paths and 3-paths. But now, what we were struggling with for a long time was like, how do we show this is non-trivial? Classically, this is done with a lot of combinatorial group theory. But David recently released this note solving the long-standing open problem of whether the suspension of a set is the one type, and that it also proves this theorem, which is super useful for us. So if you take a span of 0 truncated maps of one types, so it could be you have a diagram of groups and an inclusion, so monomorphisms of groups, and look at the classifying types, you get such a span. Then the push out, which computes the amalgamated sum of groups or the classifying type thereof, that's again a one type, and the inclusion maps are really 0 truncated, so the groups, the fundamental groups of A and B will include into the amalgamated sum. Okay. So now the way we can prove that BH is a one type and is non-trivial is to rewrite it as this push out. So we introduce these intermediate hits, which are the sub-hits. So you take a subset of the constructors. And so I list some of the generators, and then I take all the constructors that only mention those generators. So for instance, let's see, BAB, that would include A, B, and the relation that says that B is the commutator AB. Because those are the ones I can say using only A and B. And for instance, AC will only include the generator A and B, but not any of the higher relations. So that's a free group on two generators. Right. And it's super easy to see that you have this kind of push-up situation, because I just take this collection of constructors, this collection of constructors, and I identify them over their intersection, and then I get all I could get altogether. So that's clear that we have these push-up descriptions. And also this type, it was the BAB, that's a so-called H&N extensions, which is a classical topic in combinatorial group theory, named after Hickman and Neumann. And you can do those in HoTT, that there's a co-equalizer, classifying types in unpointed types. Forget about the point. So that happens to be a so-called Baumschlag solid type group. And again, from David's theorem, we get that this type is a one type. This inclusion is zero truncated, so it really is a subgroup that has the free group on one generator, so the integers, it's a subgroup there. And you also have a section retraction for the other generator, the new generator A. So that's good. And that tells, now we apply the theorem to this diagram up there. And then suddenly we know that the inclusion from AB into ABC and BC into ABC, they're zero truncated, and this kit is a one type. Okay, now we need to do the other part. We're not done yet. We need to know that the inclusions of the free group on two generators into something like BABC is zero truncated. That we don't know yet. That's the next slide. Yeah, so it makes you see that that map is zero truncated. But now that follows from another famous thing that we do in HoTT in descent. So we have a commuting cube. So you take these subkits, and I want to know that this map is zero truncated. And so the back faces are pullbacks, the top and bottom faces are push-ups, and then the descent says that all the vertical squares are pullbacks, and then since one of these is subjective, then this is zero truncated, and this is zero truncated as well. And yeah, so it's totally beautiful, completely sidesteps classical combinatorial group theory. Okay, here's some other things we've done. You can ask me about them or read them, and I'll stop here. Thank you very much.
I'm totally ignorant on this subject, but one thing that occurred to me is that this dodecahedron related group basically disappeared because you introduced commutativity, essentially. It occurred to me that this dodecahedron related group, it basically disappeared because you introduced commutativity as a consequence. And I wonder if that is a concept in group theory.
Yeah, no, that's perfect groups.
Okay.
Yeah, that's one where the abelianization is trivial. Yeah. I think I said that, but it's it may have gone by too fast.
More questions?
Yeah, so the point is that acyclicity is includes being the fundamental group being perfect, but it's also much more. So one of the things to mention here is that acyclicity is, with Whitehead's principle, so classically equivalent to having no homology, and homology is also a way of sort of abelianizing the fundamental group, and so you also get that all the higher homology groups of your group vanish.
This is like a higher group alternative to the perfect.
Yeah.
Another short question. Just a quick one. Are there connected types with perfect fundamental groups which are not?
Yeah.
Okay. So
yes, like this. This hatchet type is an example, and also when we even BA5, A5 is a perfect group, or any AN with n at least 5 is perfect, and so take BAN and it's perfect. So one thing that I have here is that it's a famous theorem that they take B sigma infinity. So that's my name for the co-limit of the classifying types of symmetric groups. The plus construction should be equivalent to the connected cover of the underlying type of the sphere spectrum. And David has proposed a map here, and we also have a construction of this plus construction. The plus construction is supposed to factorize the terminal map from any type into an acyclic map followed by a right class in a certain factorization system that we don't know whether exists. But we can construct it, let's see, for BA5. So we can construct BA5 plus, and that already gives lots of plus constructions. So we have this B sigma infinity plus. So we don't know whether this is an equivalent. So yeah, something to look at.
Thanks.
Yeah.